Amide chemistry synthesis of benzoylamino acids. The purpose is to convert the amino acids such as glycine, alanine, and valine into their benzoyl amino acids derivatives by reacting the amino acid with a benzoyl chloride and to compare the results of the three corresponding IR, C13 NMR, and proton NMR. Glycine, alanine, valine will react with the benzoyl chloride in the presence of an alkaline catalyst yields the benzoyl amino acid. When the amino acid is in the sweeter ionic form, it is in water solution. This nitrogen has no non-bonding electron pair and is not nucleophilic. Using sodium hydroxide as an alkaline catalyst in a reaction converts the amino acid into a nucleophilic form, and the amino group bearing the electron pair readily attacks benzoyl chloride to initiate amide formation. The equation for glycine, alanine, and valine are shown on the PowerPoint. For the mechanism of amide synthesis, the R represents hydrogen for glycine, methyl for alanine, and an isopropyl group for valine. First, there is a proton transfer so that the nitrogen becomes nucleophilic and the lone pair attacks the benzoyl chloride. Later, the chloride ion leaves. Then the chloride ion took the hydrogen away from the nitrogen to form the amide. For the technique, it would be microscale recrystallization. The only condition is that the solid must be less than 300 milligrams. First, dissolve the solids and boil to remove impurities by pouring the solution into clean flask using filter tip pipette. Then, slow cooling the solution. Collect the recrystallized solid using a Hirsch funnel.
The equipment needed for this procedure: centrifuge tube, Pasteur pipette, vortex machine, Hirsch funnel, filter flask, hot plate, graduated pipette, 30 milliliter beaker, test tubes, Nort pellets, and filter paper. Procedure: begin by placing 2 millimole of crystalline glycine, alanine, or valine, 1.6 milliliters of water, and 0.4 milliliters of 6M sodium hydroxide solution in a 5 milliliter centrifuge tube. Cap the tube and shake until the amino acid dissolves. Next, measure 0.26 milliliters of benzoyl chloride with a graduated pipette and quickly add this to the amino acid solution. Cap the tube and place this in a vortex machine for about 1 minute. Once the mixture is acidic, add about 0.4 milliliters of 6M sodium hydroxide to maintain an alkaline pH. The reaction is complete when a clear yellow solution forms and there are no oil droplets at the bottom. If any precipitate is present, filter this out with vacuum filtration. Add 0.4 milliliters of water to a 30 milliliter beaker. Cool this beaker in an ice bath and then add 0.4 milliliters of concentrated hydrochloric acid. Pour the reaction mixture in while stirring. It may be necessary to add another 0.1 milliliters of sodium hydroxide to maintain an alkaline pH here. Collect the solid by vacuum filtration and save the filtrate for later use. You will get a white powder precipitate. Turn off the vacuum and wash the crystals with about 1 milliliter of diethyl ether. Then remove the ether in the funnel by turning on the vacuum. Repeat this ether wash 2 more times. If colored impurities are present, recrystallize the crude product using a 1:1 ratio of ethanol to water as the solvent. Place the solvent, crystals, and a boiling chip into a test tube and boil this in a steam bath. Add about 10 to 15 Nort pellets and heat for 1 to 2 minutes. Using a Pasteur pipette, transfer the solution to another test tube and slow cool. Once recrystallization is over, collect the product by vacuum filtration. Allow the benzoylamino acid product to dry, preferably dry overnight. Weigh and obtain a melting point, and also calculate the percent yield of your product. Lastly, perform a spectroscopic analysis of the product. All the reactions are 1-to-1 reactions, so the limiting reagent is benzoyl chloride for all three. For benzoyl glycine, mass of the reactant was 0.302 grams, mass of the crude product was 0.765 grams, and mass of the purified product was 0.7 grams, with an overall percent yield of 57.85%. The melting point was in between 168 to 191 degrees Celsius. For benzoyl alanine, mass of the reactant was 0.256 grams, mass of crude product was 0.218 grams, and mass of purified product was 0.58 grams, with an overall percent yield of 50%. And the melting point was within 120 to 122 degrees Celsius. For benzoyl valine, mass of the reactant was 0.418 grams, mass of the crude product was 0.55 grams, and mass of the purified product was 0.213 grams, with an overall percent yield of 27% and a melting point in between 110 to 119 degrees Celsius. Overall, the percent yields were low, but that was expected for these reactions. Less product is usually recovered. For benzoyl glycine and benzoyl alanine, at around a 50% yield, actually reflects well upon the procedure. Benzoyl valine was significantly lower at around 27%, which may be the result of impurities trapped in the recrystallized product. This is probably due to an error during the slow cooling process, such as going too fast. Better slow crystallization allows for maximum purity.
For the IR of benzoyl glycine, we have three major peaks. Beginning with the secondary amine, at a frequency of 3335, we have a stretching vibration type and a strong, sharp peak. For the alcohol, we have a frequency at 3071 and a stretching vibration type and a strong, broad peak. For the carbonyl, at 1740 frequency, we have a stretching vibration type and a weak, sharp peak. For the proton NMR of benzoyl glycine, we have five major peaks. A at 11 ppm, integrating for 1 and having a doublet. B at 3.8 ppm, integrating for 2 and having a doublet of a doublet. C at 8 ppm, integrating for 1 and being a doublet of a triplet. D at around 8 ppm, integrating for 2, being a triplet. And E at 7.6 ppm, integrating for 3 and being a doublet of a triplet. For the proton NMR of benzoyl glycine in deuterium, we have five peaks. A at 7.8 ppm, integrating for 1 and is a doublet. B at 2.5 ppm, integrating for 1 and is a singlet. C at 7.4 ppm, integrating for 1 and is a doublet. D at 4.0 ppm, integrating for 2 and is a doublet. And E at 7.4 ppm, integrating for 3 and is a triplet. In the carbon NMR for benzoyl glycine, we have 7 peaks, beginning at A at 172 ppm, B at 41 ppm, C at 167 ppm, D at 143 ppm, E at 127 ppm, F at 128 ppm, and G at 132 ppm. In the COSY NMR for benzoyl glycine, we have two major peaks. For the alcohol, just before 4 ppm, and the group just before 8 for the benzene. For the IR of benzoyl valine, we have three major peaks. For the secondary amine at 3298 frequency, having a stretching vibration type and a weak, sharp peak. For the sp3 carbon, with the frequency at around 2962, and this also having a stretching vibration type and a weak, sharp peak. And the carbonyl at around 1722, having a stretching vibration type and a sharp, strong peak. For the proton NMR of benzoyvaline, we have multiple peaks. For group A at 9.6 ppm, integrating for 3 and is a triplet. Protons B at around 2.1 ppm, integrating for 1 and is a multiplet. Proton C at 2.5 ppm, integrating for 3 and is a doublet. Protons D at 3.3 ppm, integrating for 1 and is a singlet. Protons E at around 4.2 ppm, integrating for 1 and is a triplet. Protons F at around 4.4 ppm, integrating for 4 and is a multiplet. Group G at 7.8 ppm, integrating for 2 and is a multiplet. And protons H at 8.4 ppm, integrating for 1 and is a doublet. For the proton NMR of benzoyvaline and deuterium, we have groups A at around 9.5 ppm, integrating for 3 and is a triplet. Proton B at 2.1 ppm, integrating for 2 and is a multiplet. Proton C at around 2.5 ppm, integrating for 3 and is a doublet of a triplet. Proton Z at 4.2 ppm, integrating for 1 and is a doublet. Protons E at 7.4 ppm, integrating for 3 and is a multiplet. Protons F at around 7.8 ppm, integrating for 2 and is a multiplet. And protons G at around 3.6 ppm, integrating for 1 and is a singlet. For the carbon NMR of benzoyvaline, we have peak 1 at around 175 ppm, 2 at around 168 ppm, 3 at around 133 ppm, 4 at around 131 ppm, 5 at around 128 ppm, 6 at around 127 ppm, 7 at 57 ppm, 8 at around 31 ppm, and 9 at around 18.5 ppm. In the COSY NMR for benzoyvaline, we have two significant peaks. For the group just before 8 ppm for the benzene ring, and the group at around 1 ppm for the alcohol. In the IR for benzoylamino, we have three significant peaks. For the secondary amine, at around 3366 frequency, we have a stretching vibration type with a strong, sharp peak. For the carboxylic acid alcohol, we have frequency of 2932, a stretching vibration type, and a strong, broad peak. And then for the sp3 carbon, we have a frequency at 1449 with a bending vibration type and a medium sharp peak. In the carbon NMR for benzoylamino, you have carbon A at 132 ppm, carbon B at 167 ppm, carbon C at 134 ppm, carbon D at 127 ppm, carbon E at 128 ppm, carbon F at 17 ppm, carbon G at 54 ppm, and carbon H at 174 ppm. In the proton NMR of benzoylamino and deuterium, we begin with proton A at around 4 ppm, integrating for 1, it is a doublet. Proton B at around 7 ppm, integrating for 2, is a multiplet. C at around 7 ppm, integrating for 3, and it is a multiplet. D at around 8 ppm, integrating for 1, and is a doublet. And F at around 1 ppm, integrating for 3, and is a multiplet. In the proton NMR of benzoylamino, we have many peaks, beginning with A with a chemical shift of around 4, integrating for 1, and is a doublet. Protons B at around 7 ppm, integrating for 2, and is a multiplet. C at 7 ppm, integrating for 3, and is a multiplet. D at around 8 ppm, integrating for 1, and is a doublet. E at around 8 ppm, integrating for 1, and is a multiplet. And F at 1 ppm, and integrating for 3, and is a triplet. In the COSY NMR for benzoylamino, we have two significant peaks, beginning with the peak near 8 ppm for the benzene ring, and the peak at around just before 2 ppm for the alcohol.